So, if you would recall, we've been wanting to describe subspaces of vector spaces. And we started off by describing subspaces of Rn. And we'll talk today about why all we need are subspaces of Rn. The way we want to describe a subspace is to use a basis, which is a linearly independent spanning set. So the setup is that we get the span of a set of vectors will always be a subspace. And what we want is to take that spanning set and whittle it down to a linearly independent spanning set that we can call a basis. So these will be the building blocks for every vector in the subspace. This is kind of like looking for the prime numbers. The prime numbers are the building blocks for all the numbers. We can write every number as a unique product of the powers of prime numbers. So in the same way, we want to find out what the basis vectors are for a subspace. So we take the spanning set and we cut it down to a basis, a linearly independent set, by pulling the pivot column, by putting all the basis vectors into a matrix and taking out the pivot columns. Once we have a basis, every vector in the subspace will be a unique linear combination of the basis vectors. We get every vector because we started with the spanning set. We get a unique linear combination because the vectors are linearly independent. Those are the two things, existence and uniqueness. And moreover, the scalars that we use in the unique linear combination of the basis vectors are called the coordinates of the vector relative to the basis. So that's where we're at right now. We want to be able to write everything in the subspace as a unique linear combination of some basis vectors. That is, we want to be able to write the coordinates. The reason that the coordinate map is so important is that the coordinate map will tell us how to get from non-Rn vectors to Rn vectors. So that's kind of the big deal about coordinates. So just kind of looking ahead, if we talk about the big deal about coordinates. We'll take a set of vectors that aren't in Rn. We start with a vector space that's not Rn, and then we implement a coordinate map. And all of a sudden, our vector space just looks like Rn. So this is what we're trying to go for. We're trying to take a vector space that is not just vectors in Rn, not just columns of numbers, and use a coordinate map to get ourselves to Rn. For example, if I have a vector in here, let's suppose instead, if this is not Rn, let's suppose that this is the vector space, it's a double P, and then a subspace 2. This is a set of all polynomials of degree at most 2. So polynomials with degree less than or equal to 2, that forms a vector space. A basis for this vector space so I have to write down vectors that are in P2. This is an example of something that is not Rn. So it would be 1t and t squared. Every polynomial that is of degree less than or equal to 2 is a unique linear combination of these 3 vectors. They don't look like vectors in Rn because we're not in Rn. So if I have a vector up here, say x, I'll use the usual thing is to call them p for polynomial. I should follow convention. if P of t is 1 minus 4t squared, I can write the coordinates of P relative to this basis and say this P of t, this polynomial corresponds to this vector. The coordinates of P relative to some basis will be 1 of this first vector, none of the second vector, and -4 of the third vector. That's the game we want to play. That's why we care about coordinates so much. That's why we need to describe subspaces with a spanning set and cut that spanning set down to a linearly independent spanning set called a basis. I inadvertently named this basis B. Any questions? This is what's sitting behind pretty much all of chapter 4. This is what's driving what's going on. We want to find the coordinates relative to a basis. And when we want to do that, we're just trying to write one vector as a linear combination of the other vectors. And that's something that we did on the first day. So at the beginning, when I said this is the thing that's going to drive this entire class, I ain't lying. That is the one thing that we just do. We're solving systems because that's solving vector equations. That's writing linear combinations and all that. Linear combinations of a set of vectors or linear combinations of the columns of a matrix. Any questions on the big picture of what's going on? How's everybody? Because we've only got 3 weeks to go. Only 6 more meetings. So getting down to the end. All right. So with all this in mind, so I got that vector. This vector is the linear combination of it's this polynomial written as a linear combination of these 3 basis vectors. So I need the polynomial 1 minus 4t squared is 1 times the first vector, 1 times the first basis vector, which is a 1, plus 0 times the second basis vector, which is a t, minus 4 times the third basis vector, which is t squared. So I just wrote 1 minus 4t as a linear combination of these basis vectors. And so I just pull out those coordinates, 1, 0, -4. The square on the right, this square represents Rn. And this square here, so in this case, polynomials with degree less than or equal to 2, since there's 3 vectors in a basis for P2, over here on the right, in this example, we map this over to R3. So we'd say that the set of the vector space of polynomials of degree less than or equal to 2 is isomorphic to R3. It's not equal to R3, but we can make it look like R3 with a coordinate map. No subspace H's running around here. Any questions? Great. Let's pause the intro video and switch over to talking about homework from chapter 2.8 or section 2.8 and 2.9.